Lovely evening, everyone. As some of you have asked that you wanted to know about interprocessor connections, I'm going to tell you in this class about the same. So when you are using number of processors, you're using more than one processor to speed up your computer or whatever, you need to connect the processors. Only then there is some means of communication between them, and only then it is going to be of use to you. Otherwise, if there is no sort of communication or connection between them, what is the use of using so many processors in your system? So, to perfectly establish the working of multiprocessors, you need to connect them. And the connection between more than one processors, or the connection between multiple processors, is nothing but your interprocessor connection. So, is there just one way in which you can connect these processors? It's obviously a no, right? So, there are a number of ways in which you can connect processors. And we will be talking about a few of them, which will be useful for your examinations. So, one is the first one we're going to look at is the single bus bar interconnection. I'll just write down all the names and then we'll go into the depths. Or should I explain this first? Explain this first? So the first type of connection we're going to talk about is the single bus bar interconnection. So as the name itself suggests, you can see it, single bus. So buses, I've already told you, are just interconnection between whatever components you're having in your architecture, in your computer architecture syllabus. I've already told that before. So single bus. So there is just a single bus. There is a single line of interconnection between the various processors. So I have my processor 1, I'll call it P1, and I have my processor 2, I have my processor 3, and here is my memory. So I need to connect all the three processors to the memory. So what do I have to do? I'm using a single bus. The single bus connects all the three processors to the common shared memory. I've already told you one point before. There are loosely coupled processors and tightly coupled processors. Loosely coupled processors are nothing but, I've told you that difference. So based on that concept, you're going to have this. So processor 1, processor 2, processor 3, they're having a common shared memory. Common shared memory. It's your example of your tightly coupled. So this is the single bus bar arrangement. But a few problems arised when they began to implement this arrangement. It was when processor 1 actually wanted to communicate with the memory, it was not possible because it was either busy with another processor 2 or processor 3. So when one processor is already using the memory, it is not possible for another to access the memory. This is where a problem comes, and to overcome this, not other type of interconnection, under the same single bus bar interconnection, that they made a slight change by adding a cache memory to each and every processor. That is one way, and another way was each processor had its own set of components. For example, you have processor 1. You had an I/O processor for that, an I/O interface, an input-output interface, an input-output processor, the processor itself, and then comes a cache memory. So each processor had a set of its own components. So this was one way in which they slightly improvised the single bus data interconnection. But however, this type of interconnection is not suitable for us, because in today's computers it is very unlikely that you just use just one or two things. It's not really easy. If you are going to your processing speed, though your processor might be too good, and if your communication, if your lines are not so good, what is going to happen? Your system is going to slow down. Even if you have a great processor, if it is just unable to communicate with the memory, what's the point of having a good processor? So, with a good processor also comes the need for a good data type of for a good type of interconnection. So this is the single bus bar interconnection. I'm gonna write everything on the top right, so that you can just have a look at the end of the class. The first one is single bus bar. Now comes the second one. Second one is a multi-port network, and there is another concept called priority, which I'll tell you in my next class, or today if there is time left. So the next comes is multi-port networks. So multi-port networks are just one step ahead of this single data bus interconnections. So, for example, you have 4 processors. You have 4 processors, and I have 4 CPUs. I have 4 processors and I have 4 CPUs. So what am I gonna do is, let me write this as P1, P2, P3, P4, which are my 4 processors. So, and these are my 4 memories. This is my memory module 1, memory module 2, memory module 3, and memory module 4. So I have these 4 processors which I have to connect with their different memory modules. So if it was a single bus type, you can just connect one single bus and every processor is connected like this. That will be the single bus data type, the single bus type of processor interconnection. But we are dealing with a multi-port network, which is, as I already told you, a slight improvisation of your single bus data structures. This is very efficient. This is very efficient because each processor is connected to each and every memory module. See, processor 1 is connected like this, again connected to 2, connected to 3, and connected to 4. And the same with P2. P2 is connected to 1, is connected to 2, is connected to 3, is connected to 4. There is gap between them. P3 is connected to 1, P3 is connected to 2, P3 is connected to 3, P3 is connected to 4. So each and, I'm not drawing it for the fourth one, however, as you know, is connected to 1, is connected to 2, connected to 3, and connected to 4. Each and every processor is connected to a memory module. So just think, your processing speed is fastened, your speed is fastened or not? It is fastened. So, because each and every processor has an access to a memory module, the speed has drastically increased from what you will be having in a single data bus type of interconnection. So this type of interconnection is very efficient, but just look at the number of connections. It becomes really complicated and it becomes very expensive. Especially when you have large number of processors and you have many memories modules to interconnect with the processor, just think about the cost you are going to rise. So this type of interconnection, though efficient, is not employed in most cases. It is employed only when you have very less number of processors and less number of interconnections to make. So at the end of the day, in a nutshell, multi-port networks are efficient, but you don't employ them. Remember like that. The next type of interconnection we are going to deal with is the crossbar switch. So the crossbar switch, you will enjoy drawing this in your exam. You have processor 1, you have processor 2, you have processor 3, you have processor 4. I have my memory module 1, memory mod 2, memory mod 3, memory mod 4. This is the crossbar switch. As the name itself suggests, there is a switch in this type of interconnection. There is a switch. Visible at the back. So each processor is connected in such a way that there is a switch at every junction. Every junction has a switch. So what is the purpose of the switch? The switch has a logic, a multiplexer, which determines what actually should be passing through that. So if I want processor 1 to be active, if I want processor 1 to communicate with module 1, this switch is going to tell, give processor 1 to module 1. So each switch has a logic, and that switch determines which processor is going to have which memory module. So if you look at this, the first thing that comes into your mind is your multiport network. But the difference from your multiport network and this is the reduction in the number of connections. So a crossbar switch is a really good improvisation of what your multiport network is. However, from our exam point of view, the first and the second are more important, although you might be asked to explain all the 5 types of interconnections. So just go through this. This is your crossbar switch. Each switch has the multiplexer which determines which processor accesses which memory. So this is all about your crossbar switch. The next type of interconnection is your switching networks. Or switch networks. To explain this, let me just ask you a simple question. You have your switchboard. You have switches there. So in that switch, you have an on position and an off position, right? So an on position you take it as 1 and an off position you take it as 0. This is the same logic, there is no difference in that. That is why it is called switch networks. So if I am this is my value A. This is my value A. A value depends on how I switch it. I can switch it either to be 1 or I can turn the switch to 0. It is a switch. As I am telling you, it is a switch. I can either make it 0 or I can make it 1. So this is a simple type of a single switch. A single switch is what I am talking about. But just think about that logic which has excuse me, a number of switches connected. For example, I want the output logic as 0, 1, 0. This is my required output logic. So this will be my first starting A. 0, 1, 0, 1, 0, 1. Again for this 0, 1, 0, 1. Again for this 2, 0 1 0 1. For this too, 0 1 0 1. So if I want 0 1 0, the first switch is going to be 0. The next switch should be 1. So this is it comes till here and it switches to 1. And again the next switch, it has to be 0. Don't write it at the upper part. Always see like this. Divide it like this. If you are writing from 0, go to the upper one. If you are taking from 1, go to the down switch. That is an important part you have to consider while joining switch networks. For example, he asked you in the exam, give me the output logic for 1 0 0, then you have to take care about how you are going to connect the switches. You yourself are going to make this pattern, however, but you have to see that if you are connecting from 0, go to the up one. If you are connecting from 1, go to the down one. So here you have connected to 1, and for this particular switch there are 2 daughter switches. So the first daughter switch is, I am going to use it when I am writing from 0. The second daughter switch I am going to use when I am writing from 1. So from 1 I am going to connect to 0. So comes till here and then 0. So first one is 0, second one is 1, again third one is 0. So the output in that line will be 0 1 0. This is how your switching logic is done. So based on the required output you can change the switches. So there are a few disadvantages in using these switches, because when you want two different outputs, like say you are already using this particular switch, this second one. At the same time, can I get an output 0 or can I get an output 1 0 0? Can I get it? I can't, because this switch, it is already engaged here. Even if I am using the same 0 logic here, I cannot change this value, this switch value. So at particular points there is a clash, and that is why those switching networks are very easy to understand are not used, because of a few limitations. The next thing we are going to learn is hypercube interconnection, which is used even in Intel processors today. Hypercube interconnection. This is also called binary cubes. So looking at the name, any ideas coming to your minds how the structure is going to be? Yes, exactly. It is going to look like a cube. Cube, hypercube. The name itself suggests that the interconnection looks like a cube. How does a cube look like? Like this. So every interconnection in hypercube connection will look like that? There is no other way? Every connection is supposed to look like this? No, it doesn't have to. Because the dimension of the cube depends upon the number of processors. If I have a single processor, I don't have to perform any interconnection, and even though I am employing this hypercube interconnection, the processor is just going to be like this. This is my processor, I am numbering it 0 0 0. That is how my processor is going to look, even if I am employing hypercube interconnection. If there are two processors, say 0 0 0, 0 0 0 is my first processor, and 0 0 1 is my second processor. This is the way it is going to look if I am employing this, because there are only two processors. How else am I going to connect it? I have to use this only method. Clear? Now comes question. If there are, see, it is applicable for processors if they are in powers of 2. This is 2 power 0, single processor. This is 2 power 1, 2 processors. Next comes 2 power 2 is equal to 4 processors. So, single dimensional, this is, if I am having 4, this power 2, it means 2 dimensional. My processor connection is going to be 2 dimensional. See this. I have 4 processors, which is 2 power 2. So 2 dimensional. So 0, 0, 0, 0, 0, 1, 0, 1, 0. I don't have to use 3 zeros. I can just use this. I can just use 2 numbers. I can represent it with 2 bits. Right? So this connection is going to be like this, 2 dimensional. If there are 2 power 3, 8 processors, 2 power 3, what does 3 indicate? The dimensions. The dimension of the cube which is going to be used. So if there are 8 processors, it means my interconnection structure is going to be 3 dimensional. 3 dimensional. So shall I rub this part? Okay. So if there are 3 processors, observe this one. The previous ones are not really important for your exam. Processor 1, processor 2, processor 3, processor 4. The first phase of your processors. The second phase of your processors lies inside. Why? It is a 3-dimensional cube. See this? If you look at this, it's just an unarranged patch. But however, just once you draw the lines, it's going to be clear. That's it. That's it. That is your interconnection. And be careful while numbering. 0, 0, 0, 0, 0, 1. Go to the back one. 0, 1, 0, 0, 1, 1. Start from here. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So I'm numbering the 8 processor with different bits, and this is how I'm going to interconnect 2 power 3, a 3-dimensional. So just a simple thing, this is applicable for powers of 2, that is point number 1. And whatever the power of 2 is, that is going to be the dimension of your interconnection cube. Cube is there. The dimension of the cube is given by the power of 2. So these are the different types of interconnections. Just have a look again. First one is single bus bar, in which a single bus connects every processor. What is the disadvantage of this? What is the disadvantage of this? It is because if one processor is communicating with the memory, another processor cannot communicate. And this priority of which processor should get to the memory first and which should get second, all that I will be explaining you in priority classes. In the next class I will take that. For this class, single bus bar, there is only a single bus. Processor communication is difficult when one processor communicates, another cannot communicate with the memory. That is point number 1. That is single bus bar. Multiport network. Every processor is connected to each and every memory module. But though it is efficient, you cannot employ it because the connection is complex, and also it makes your device very, very expensive. And next comes crossbar switch, which is an improvisation of your multiport networks. It has multiplexer logics at the every junction of the processor and memory interconnections. The next comes is switch networks. Switch networks are actually very easy to implement. However, there are a few limitations, so that which is actually stopping some specific outputs to come. There is a clashing thing in switching networks. The next comes hypercube interconnections, which is used even in Intel processors. I don't remember the processor name, something PS. I'll refer it and I'll tell you. So it is used even in Intel processors. In a few Intel processors, this type of interconnection is also employed, especially when the number of processors is equal to 7, 2 power 7. Imagine that. So this is all about your processor interconnection. This answer is very important, and I hope you'll do well in your test.